Welcome to the Fractional Calculus seminar. Today we have Professor Christian Glusa from Sandia National Laboratories. Christian Glusa is a staff member in the Center of Computing Research at Sandia National Labs. His research interests include scalable linear solvers such as multigrid and domain decomposition methods and their application to problems in electromagnetics and fractional order equations. Christian received a PhD in applied mathematics from Brown University in 2017 and an undergrad degrees from Karlsruhe Institute of Technology and École Polytechnique in 2012. We are very happy to have you here. You may please begin your talk.
All right. Well, thank you very much for your introduction. I'm not a professor, despite what you stated. Sandia is a pure research institution, so no professors. All right. So if you could switch to the first slide, please. So I won't go much in terms of like motivation or anything. I'll just jump right in and sort of like just to get started, fix some of the notation that I will be using. I'm sure that you're all already pretty much familiar with all of this, but let's just make sure that we know what all the symbols mean. So we want to solve a non-local or an integral type of equation on a bounded domain. So our domain will be omega. We will have a kernel function gamma, which sort of like encodes these interactions over a distance. And because we have interactions that are non-local, we will require, if you want to impose some sort of boundary condition or something that sort of like looks like a boundary condition, well, these are non-local interactions, so we'll have to instead enforce something on sort of like a delta collar around our domain. And here delta is the so-called horizon, which is essentially the length scale over which we have these non-local interactions. Now, delta can be finite, but it can also be infinite. In which case, this interaction domain, what I term omega I, would be the entire complement of our domain. So we would be imposing some sort of volume condition on the entire complement of the domain. Now, the operator that we care about looks a bit like a Laplacian operator in some ways. So it's really this sort of like a weighted difference between the value of our unknown function u in points x and y weighted by the kernel function. And so the types of kernel functions we want to like be as general as possible within this sort of like framework of Laplacian-like operators. And so we'll take this form that is down below. So we generally will have some sort of prefactor. This Feigen, you can sort of think of it like a diffusion coefficient. Now, this is a two-point function. We depend on 2 points in the most general case. The next term that we will have in this kernel will be some singularity of some form. And the strength of the singularity in most general sense can also vary in space. And finally, we have this sort of cutoff term or indicator function that essentially like limits us to interactions only over a range delta. And I mean, there are some conditions that we probably need to enforce on this type of kernel function. For example, phi, we probably want this to be positive, so that overall we have a nicely sort of like a well-posed operator. We also will have to require that phi doesn't actually blow up, so there's no singular term in phi itself. And we will see there are some other conditions on how regular these coefficients phi and beta actually are. So examples for the types of operators that we will cover with this, there's obviously the integral fractional Laplacian. That is the case where the strength of the singularity is fixed. So we will have the beta is equal to the spatial dimension plus 2s, where s is then termed the fractional order. And in that case, delta really is infinite. So we're working on the entire space. And phi will be simply a constant. In this case, this is just a normalization constant that doesn't vary in space. If you want to make things a little bit more interesting, then there's the so-called tempered fractional Laplacian, where we apply some additional tempering to make sure that all the moments of our or higher moments of our operator are still well defined. We can also apply some truncation, so we can use the same type of kernel function, but then truncate in space and only consider finite range interactions. And we can also make life more interesting by allowing the strength of the fractional order to vary in space. So we could have something like beta being equal to d plus 2s, where s now depends on x and y, or maybe only on x. And on the other hand, there's also this big family of integrable kernels. So something like a constant kernel or this sort of like inverse distance kernel fall into this family of kernels that we want to consider. And this inverse distance kernel sort of like motivated in some ways by paradynamics. In terms of normalizations of these kernels, very often we will pick this prefactor phi to sort of in a way so that allows us to recover the classical Laplacian in certain parameter limits. So for example, for the integral fractional Laplacian or the truncated version, we'll probably pick the prefactor in a way so that if delta goes down to 0, we'll recover the classical Laplacian. Or if s, the fraction order, goes to 1, we'll recover the classical case. On the other hand, for the fractional order going down to 0, we then often recover the identity. I should probably also say this kernel, I mean, it's quite potentially quite singular, and so we might not be able to take the integral in the sort of like classical sense, but we have to instead take it in the principal value sense, which means nothing else that but we're sort of cutting out a little ball around the point on the singularity where x is equal to y, and then that integral we can evaluate, and then we shrink the ball down to 0 and define the integral in the limit sense in that way. Next slide, please. All right. So the types of problems that we might care about, there's sort of like a sequence of problems that are of interest to us. The simplest one is this nonlocal Poisson equation at the top, where we, as I alluded to earlier, impose a volume condition on omega I, which might be the entire complement of omega. And then associated with that, we obviously can also like then look at the sort of like associated parabolic equation, so this heat equation in the next bullet point. And then we also might want to solve some inverse problems. So either like a source control sort of problem, or what is currently a lot more of interest to me, these parameter learning problems where we try to figure out, okay, what are the actual parameters that we choose in our kernel function based on some given experimental data or like observed data UD. Now, what I have on the slide is sort of like the simplest possible case where we really have like data given in a sort of like continuous sense in our entire domain. You could also sort of think about like sparse observations, or maybe you already know something about some noise that is that you will probably have in your observation, and we're also sort of like moving more into a sort of like a Bayesian or UQ framework for these types of problems. But what all of these problems have in common is that you will have to assemble and then solve a non-local equation in discretized form at least once. For these sort of like the last two problems on the slide, you have to solve a non-local problem several times. You might even have to like assemble this different problems for different parameters several times. And so by the end of the day, if you want to convince any engineer to finally actually use these types of methods, then you really cannot convince them to do so unless the sort of like the complexity and the memory usage of these methods sort of matches what you would get for a classical PDE type model. So something that scales like order n log n, but there might be some different power law or like some different exponent on the logarithmic term, but effectively you want something that more or less scales linearly. Next slide, please. All right, so we'll talk very quickly a little bit about the well-posedness of some of these problems. So this is the sort of like subset of variable order fractional problems. So essentially, I mean, you have to impose some amount of additional regularity, and that's the sort of like a result for that. The upshot is that you need to either, so if you're in a most general case where S and phi, so sort of like your fractional order and the sort of diffusion prefactor, where they depend on X and Y on both of these variables, then you effectively need to control or have regularity on the antisymmetric part of these coefficients in the limit of x going towards y as we're sort of like approaching the singularity. Now, in particular, what that means for the case of where like say the fractional order only depends on a single variable, where it only depends on x. This then translates to the fact that you need some amount of Hilbert regularity on S. All right, next slide, please. All right, so once we have convinced ourselves that we are in a well-posed scenario, we then are off to the races. We'll do what we always do. We want to use finite elements, and we will derive the bilinear form associated with our problem by via integration by parts, or sort of like the non-local equivalent of integration by parts. So we multiply with a test function that is nice and smooth enough, and then do some summation by parts and rewrite our double integral. This will be posed on the sort of associated energy space, where the energy norm is defined in the center of the slide, just again via a double integral with respect to the kernel function. And what this energy space really boils down to is then either an L2 space on a domain for integrable kernels, or a fractional type cellular space. The case where the fractional order sort of like varies in space is a bit more interesting, because you can't just reduce it to one of these two cases, but it's sort of like a sort of like interesting looking variant of this fractional type cellular space. Now we already see that there's still a massive issue in that the second term in our bilinear form, we have an integral over the interaction domain omega I, which if the horizon, if delta is infinite, that I mean, we won't really be able to represent this correctly on a computer. We can't integrate over unbounded domains, so we will have to play some tricks to like make this like transform it into something that we can actually handle. So one way of doing this is with a Gauss trick, where you effectively sort of reduce this integral into an actual like surface integral over the actual surface of your domain. Next slide, please. All right, so then we'll discretize our domain omega using simplicial elements. We can rewrite our bilinear form using sort of like a sub-assembly routine. The only difference with the classical PDE setting is that instead of like a single sum over elements, we have a double sum over elements, or like elements and sort of like surface elements or edges. And well, at this point, there's no closed form for the local stiffness matrix, so we will have to use numerical quadrature to compute these terms. And what we're already seeing right away is that, I mean, the mesh that we will be picking, there's no way that we can sort of align this correctly with the interaction neighborhood of our kernel if we're in the finite horizon case. So I have my little picture down there. I have picked some point in my domain. I've plotted the sort of the interaction neighborhood around this point, and I have the mesh, and they simply don't line up with each other. And this is important because if we then use numerical quadrature, we really don't want to integrate over the discontinuity of our kernel function, because that will really spoil the rate of convergence of our quadrature. So what we'll do instead is we will remesh the support of our kernel function, sort of like locally on an element by element basis. So what I'm showing you there is, for example, to integrate over the actual support of the kernel with respect within this little triangle on the right. We'll instead construct a retriangulation of the actual support within that element. And I mean, we're sort of making an error there because we're not integrating over the sort of like the little cap that you can see on the right. But what you can show is that the error that you commit by doing so is of lower order than what actually matters. So in the grand scheme of things, you will not see this error as the final element rate of convergence is already larger than that. So that's a permittable sin. Next slide, please. All right, so the other problem that we're still having is that we're integrating over a kernel that is quite singular. Now, we obviously have these other two terms in there that sort of like are differences now of our basis functions, and they help us to cancel some of the singularity out. But I mean, obviously, we still need to be careful if we happen to put some quadrature nodes directly into the singularity. Very bad things will happen if we divide by zero. So we obviously need to avoid that. But I mean, on a sort of like in a somewhat more subtle way, the presence of the singularity also impacts how quickly this numerical quadrature will converge towards the correct solution or towards the correct integral. And so what we do to sort of like handle this case is that we apply a trick that's sort of like well known already in the boundary element literature, and that is we transform the domain of our integration. So one of these sort of examples that I have here, where like we actually are integrating over the singularity, where like we have two elements that touch each other. We transform this into a hypercube and then use the Jacobian of this transformation to cancel out the singularity. And if you then analyze these sort of quadrature rules, you then also end up with showing that the order of your quadrature rule is dependent on your element sizes, and so you have to sort of like increase the order of the quadrature rules as you refine your mesh, or sort of like it depend on the local element size. Next slide, please. All right. So the next aspect that we sort of need to address is that contrary to classical PDEs, the regularity lifting for these non-local problems is sort of limited. So in the classical world, you sort of like to think that, okay, if you have like a really nice domain, and if you have like a really nice right-hand side, and if your coefficients are all very smooth, then your solution is going to be very nice and smooth. In a fractional world, that is unfortunately not the case. So down below, I have these sort of like by now classical examples of like solving a fractional Laplacian on, in this case, that's just the two ball. So that's a very nice and smooth domain. We use a right-hand side that's just constant one. So everything sort of like seems like we're in a really nice and well-behaved setting, but the solutions really do not have a lot of regularity. I mean, they have a lot of interior regularity, but the regularity close to the boundary is really quite low. And this is also reflected in this regularity theorem, which essentially says that you at most get like a order 1/2 pickup of regularity. Next slide, please. Now, if we then consider our piecewise linear finite element approximation of the problem, obviously the regularity then also affects the rate of convergence that we can expect from a finite element discretization of these problems. And so effectively this order 1/2 regularity pickup is also our maximal pickup in terms of finite element convergence, assuming that we are on a quasi-uniform mesh. If we resolve this sort of like a very singular looking behavior close to the boundary somewhat better, then we can achieve higher rates of convergence. And at that point, life becomes a little bit tricky because I mean, obviously we want to like use like I mean, we've seen that really the boundary itself is the issue. And so if we put like really, really small elements close to the boundary, then we can get quite a bit better rate of convergence. but in dimensions larger than one, shape regularity of our elements will require us to sort of like gradually uh, transition between like very, very small elements and larger elements on the interior of our domain. And so effectively, we cannot, this sort of like still makes us lose some finite element convergence compared to what we could achieve if we, for example, fully gave up on shape regularity of our elements. But if we do that, then yeah, there's a lot of other terrible things that can happen to us. So like the upshot of the slide should be that we generally expect lower rates of convergence for these non-local problems than what we would expect for classical, sort of like in the classical PDE setting, at least under sort of like in a situation where all the coefficients are really like nice and smooth. Next slide, please. All right, so this is sort of my summary slide of what we expect in terms of rates of convergence. We have to distinguish between the two cases if we're in dimension one, so essentially like on an interval or in higher dimensions, and whether or not we are using a quasi-uniform mesh or uniform mesh, or whether we are using graded or like adaptively constructed meshes. So in the sort of like the quasi-uniform case, the rates of convergence in terms of mesh size match between one dimension and higher dimension. The same goes for the L2 error, but instead, if we then go to graded meshes, we get like the sort of like optimal rate of convergence that we would expect for these types of problems in 1D. In 2D, we have to pay a little bit of a penalty for staying with shape regular meshes. Next slide, please. All right, so we are now in a situation where effectively, okay, we've pushed our finite element method through, and we've assembled our linear system that we now need to solve. But then we need to pause a little bit and think, because depending on what the horizon is compared to the mesh size, the system might be pretty dense. So if you think about the sort of worst case scenario, that is when the horizon is infinite, well, then every degree of freedom in our system is coupled to every other degree of freedom, meaning that the matrix is entirely dense. And this means that at this point, we have already lost if we sort of want to achieve the same complexity as a classical PDE, because no matter what we want to do with this matrix, I mean, assembling it costs us at least all the n squared operations. Doing a single matrix vector product with this matrix costs us all the n squared operations. So at this point, we've already lost. So we need to like go back a little bit and think like, is there some way that we can avoid assembling this fully dense system or working with this fully dense matrix? And so what we will use instead is an approach that, I mean, in the literature comes with a couple of different names, can either be termed the panel clustering or fast multiple method or hierarchical matrix approximation in sort of like its most general form. And the idea is relatively simple. We will split our matrix into sort of entries that correspond to interactions over sort of like short distances and then long distances, or like near field and far field interactions. We will sort of like in a straightforward way, we will assemble all the near field interactions, but we will try to approximate sort of like blocks of long range interactions with low rank approximations. And at that point, sort of the name of the game then is to control the error that is incurred by doing so, to make sure that that stays below the discretization error that's already present in our finite element discretization. And so if you do that, then effectively you have constructed an approximation to this fully dense system that hopefully is a lot sparser, but has only negligible error encoded in it. Next slide, please. All right, so we'll need some infrastructure to be able to decide like where we want to approximate on our operator. So in the top left corner, what I have is a little picture of my fully dense nonlocal operator, or the discretization of a nonlocal operator. And this is a 1D example because these pictures look a little bit more digestible in 1D. In higher dimensions, they become a little bit messy. And what we want to do is now we want to decide, okay, on which blocks or subblocks of this matrix do we want to apply some approximation. And so we need to first decide, like, okay, what do we mean by subblocks of our operator? And so we need to have some way of sort of like indexing into our system or in a sort of blocked fashion. And so the way that we do this is that we first construct a so-called cluster tree. So I have sort of like two copies of my tree pasted there, one for the row space and one for the column space. And so the way that we construct this is that on the sort of like causes level, on the root of this tree, all our unknowns are in the root. And then we refine this tree based on the physical location of the unknowns. So essentially, we divide, right, this is 1D, so we divide first our tree into like all the unknowns that are like left of some separator and all the unknowns that are on the right of some separator. Now, in this particular case, I picked a mesh that's uniform in space, so this looks like fairly regular. But you can obviously also play these sort of games for adaptively refined meshes that are like where the unknowns are not nicely laid out in space. All right. And so then we have these two copies of this tree, and we can effectively then loop through these two copies and look at different subblocks of our matrix. And I mean, the subblocks clearly are nested in multiple ways. And what we can then do is we can, by looking at sort of like one of the subblocks of the matrix, we can decide whether or not we want to apply approximation to this block or not. And this is based off of this admissibility criterion, which essentially says, okay, we're looking at a particular block, say the top right block in our matrix, and we will sort of compare the distance between the sort of the unknowns in the row space and the unknowns in the column space. Are they very nicely separated in space compared to the size of these two blocks? And if that criterion is true, then we will mark this block for a low rank approximation. Now, you see essentially here in this 1D example, as we get closer to the diagonal of our operator, we can only approximate on smaller and smaller blocks. And at some point, once we're like very close to the diagonal, then, well, we will never find any blocks where we can do approximation. And so these are then the blocks where we do that we fully assemble and that are part of the near field. Next slide, please. All right, so we've now decided where we want to apply approximation. So we will want to approximate all the blue blocks, and we will just directly assemble all the red blocks. Now, in the first step, what we want to do on the blue blocks is compute something like a truncated singular value decomposition of these blocks, and then in that sense sparsify the blocks. But obviously, we never really want to assemble this block entirely in full and then apply some sort of truncated SVD to that. Instead, we want to like compute a sort of like truncated SVD-like expression for this block on the fly. So what I use for this is a Chebyshev interpolation technique, but there are plenty of other techniques out there. One technique that is really quite famous is this adaptive cross approximation, which essentially relies on sampling entries out of this block and in this way constructing this lower rank approximation. Okay, so now we've rewritten our block as the sort of like product of three matrices, one tall skinny matrix, one small coupling block in greeny here, and then the transpose of a tall and skinny guy. And in the top row, in the middle picture, I sort of tried to like visualize this and show the fact that now we have a lot more white space, so we create more sparsity in this way. And this is termed then a hierarchical matrix or an H matrix. Now we can go one step further and then also use this our tree structure one more time. And effectively, what we can do is we can write the tall skinny guys sort of recursively using the tree structure as a linear combination of the tall and skinny guys of our truncated SVD only on the leaf nodes of our cluster tree. And so this is the picture on the right, which is then termed an H squared matrix. Next slide, please. All right, so now we have constructed a sort of like very complicated looking version of our stiffness matrix. If you want to like perform a matrix vector product with something like that, in the end, it's really quite simple. I mean, we first have to perform this matrix vector product with the near field matrix, so the guys that we all assembled directly. But there are very few of those now, and so we can save that in a sparse matrix. So that's sort of like the same as what you would have in a classical PDE setting. And then we have to like sort of like loop through this tree structure and sort of like in a sort of like a two sweep fashion, sweep through that twice, and then also apply all these sort of like a far field interaction box. So effectively, this boils down to a whole lot of matrix vector products. And what I haven't shown you, but I've tried to sort of like visually convey is that we've created a lot of sparsity. And so effectively, the complexity of performing a matrix vector product with this hierarchical matrix approximation, or even the cost of assembly now scales like order n to the log 2dn, where d is the spatial dimension of our problem system, like 1D, 2D, 3D. And the other result that I'm not showing here is that you can prove under sort of like if you pick the your low rank approximation correctly and the rank of your low rank approximation, then the resulting approximation error is on the same order as your discretization error, which means that you're not spoiling your finite element rate of convergence by using this approximate operator instead of the fully assembled dense operator. Next slide, please. All right, so one quick implementation detail. I mean, this looks like there's a lot of like code infrastructure in the background if you want to do something like this. But fortunately, you can reuse a lot of pre-existing sparse linear algebra to do this. And because you can, I mean, in the end, I mean, we're having like a tree structure in there and things like that. So all of these can be well represented by sparse matrices. So effectively, you can rewrite this as one big product and sum of sparse matrices. And because obviously we care about doing this in a memory distributed fashion, there's really only two operators or two matrices in this expression that will require any sort of communication. There's one that is the near field matrix, which probably isn't all that surprising. And then the other term is this gamma guy in the middle, which corresponds to the green guys in my picture, which are the coupling blocks, sort of like the small coupling blocks in my truncated SVD that also can be sort of like encode this non-local nature of my operator. All right, next slide, please. All right, so now we're at a point where we have a fast matrix vector product, and so we can actually think about solving this linear system. And because we have a fast matrix vector product, we obviously want to use iterative linear solvers now. So the first thing that we need to think about is, well, what is the condition number of the system? And it turns out that it depends a bit on the type of the kernel and the parameters of the kernel. So maybe the sort of like the simplest case to visualize is the fractional kernel, where we know, I mean, we know the sort of like two parameter limits, like it's sort of like an interpolation between the identity operator and the Laplacian. And so it's no surprise that the condition number also sort of like interpolates between the condition number of the identity, which is one, it's a one condition operator, and the Laplacian. Um, and so depending on what the fractional order is, we'll have a more or less ill-conditioned operator. So we definitely need some sort of specialized preconditioner in order to solve this. But there are also some other cases that are perfectly well conditioned. So for example, for integrable kernels, and so with a finite horizon, the condition number is only 1 over the square of this horizon. And I would consider the horizon as sort of like a physical parameter that is like that shouldn't really change or that is not dependent on your your discretization. And so this is really an example of a well-conditioned matrix. Now, the time dependent case is sort of interesting because uh, if so if you're in the fractional setting and the fractional order isn't too high, then effectively this is a perfectly well conditioned operator, which is sort of interesting if you compare or contrast this with the classical PDE world setting. All right, so we have some situations where the condition number of our operator can be quite high, and so what we're looking for is a scalable solver or preconditioner for these types of systems. Obviously, we will look at the same sort of candidates that are scalable in classical PDE world, so either multigrid or domain decomposition. I'll mostly focus on multigrid for this talk, but I've worked on all of these by now. Next slide, please. All right, so let's get started with geometric multigrid, and I'll try to sort of like explain a little bit like how this works in a single slide. So on the finest level of this sort of like hierarchy that we have, this is our system A or A0. This is the system that we actually want to like that we want to solve. And what as a user of multigrid, what we will specify is sort of this hierarchy of coarser approximation of the same problem. So we'll have effectively, I mean, if we have assembled our problem on this very fine mesh at the top, we'll have a sort of a hierarchy of coarser meshes, and we'll assemble the same non-local operator on each and every single one of them. What we will also have is matrices or operators that allow us to move data between these different meshes. So typically these are interpolation operators, and then they're the transpose. And finally, what we will need on every single one of these meshes is a sort of like a cheap iterative scheme to sort of solve on that particular level. So typically we'll use something like a Jacobi iteration or a Chebyshev iteration, something that really only does like a matrix vector product and then does some amount of like scaling. And now the reason why this works, or why this works a lot better than just simply applying this sort of cheap iteration only on our matrix A0 is that every single level is sort of like there's a splitting of error frequencies, and every single level is good at reducing high error frequencies with respect to the mesh that's associated to this level. So something that like very sort of like very quickly those sort of error frequencies will remove really quickly on that particular mesh, but we're not good at removing sort of like slowly varying error frequencies. But the good thing is that what this sort of splitting between like high and low frequencies is mesh dependent. And so for every error frequency, there is a mesh where we can effectively reduce error quite quickly. Now, this explains why you only need very few iterations of this multigrid solver or preconditioner to effectively remove all your error and solve the system super quickly. Now, the drawback of geometric multigrid, and we'll loop back to this later, is that you effectively need you need this nested hierarchy of meshes. And if we're thinking about using sort of like locally refined meshes, then this can be a sort of a problem. Sorry, my screen just locked on my end, so I need to like. Okay, so this can be sort of complicated if you have a locally refined hierarchy of meshes. On the other hand, it's also a bit annoying to have to assemble so many non-local operators, and we don't really like sort of like tight coupling between the assembly of our discretized system and then the solution of the system. This isn't necessarily very user-friendly. Next slide, please. All right, so let's have a look at some numerical results. So this is using a geometric multigrid now. So we will outright assemble all of like non-local operators on a sort of hierarchy of meshes. For the restriction and prolongation, so for going between the different meshes, we will just use the typical sort of like nestedness of our finite element spaces. And for smoothers, what we will be using, I think for all of these examples, I was using Jacobi smoothing. I mean, essentially, you want to use something that you can still do even if you have only access to the diagonal of your operator. So something like a Gauss-Seidel iteration, for example, would be quite tricky to pull off. And as the sort of the coarse grid solver, so the solver on the sort of smallest mesh, we will simply convert the system into dense format and then apply something like an LU factorization to that. In terms of test problems, we'll look at the uh, the unit disk in 2D as our domain, and then we'll take three different types of fractional orders. So these are all fractional kernel examples. We'll either take like a low fractional order, a high fractional order, or then a fractional order that varies in space. Next slide, please. All right. So this is the first slide of these numerical results, where I show essentially the error convergence as we sort of scale out our problem. So we can see that in all of these cases, the observed rate of convergence, both in the energy norm, so in this case, a HS norms like a fractional solver space norm, or the L2 error, they all match the theoretical predictions that we made. And we can scale this out. So these are all examples. They run on a cluster that we have at Sandia. These are single core examples. And we can scale this out to something, I don't know, like a 100,000 or a couple of 100,000 unknowns. Um, and all of these examples, they used geometric multigrid. Next slide, please. So the flip side of the coin is that, well, how long did it cost us to perform this assembly? And so what I'm showing is the different curves are the time to assemble the entire hierarchy. So the non-local operators on every single level of this hierarchy. And then in the little like squares is the assembly time of the finest level. And it's not that surprising that that effectively dominates the overall assembly time. Then the little like axes show the solve time. And so we see that sort of like contrary to classical PDE world, overall solve is a lot cheaper than assembly. And I also show that the matrix or the memory usage for the operator on the finest level that's also shown in these plots. And we see that all of these essentially have a scaling that more or less matches the predicted n log n scaling, well, n log to the 2D and scaling, and D is 2, so that's a power 4 on the logarithm here. And I mean, I should have said like on the left, that's the sort of like the low fractional order. In the middle, that's the high fractional order, and on the right, that's the case where the fractional order sort of like varies in space. And what we can see is that yeah, in all of these cases, we can scale this out quite nicely. Next slide, please. Now, so all of the so far everything was on a single CPU core. What we are doing now is a weak scaling experiment where essentially we increase the computational resources that we allocate to solving this problem in a way that is proportional to the overall problem size, to the number of degrees of freedom. And so what we see is that now, I mean, our curves are still going up, and the reason for that is that by increasing proportional to the problem size, we're addressing sort of like this the n in n log n, but we're not addressing the logarithmic factor. And so what we're seeing now is the sort of like logarithmic growth of time and memory as we scale our problem out. We can see that we have the lowest sort of like time to assemble and solve the problem for the low fractional order. The time for the high fractional order is it's somewhat slower, and then there's a big slowdown when we then look at the sort of like a space varying fractional order. And the reason for that is that we're still having some issues with load balancing for this problem. Effectively, in the sort of transition region where we go from the low to the high fractional order, we probably need to like allocate more computational resources to this transition region, because what we can see is that effectively there's only a couple of sort of like MPI ranks where all of this slowdown happens, and that really caused this sort of like overall slow times. Next slide, please. All right. So I've talked a lot about hierarchical matrices, and obviously, if the horizon of your kernel is quite large or like is even infinite, then hierarchical matrices are the way to go. But on the other hand, if we are thinking like, okay, what about a situation when the horizon is sort of like very similar to the mesh size, say like 2, 3 mesh sizes, well, at that point, using a regular sparse, classical sparse matrix is definitely the way to go. So then the question is, well, okay, so we have these sort of two extremes, and at what point should we switch over from one to the other? At what point does it start to make sense as we sort of like increase our horizon? When should we start using hierarchical matrices? And so what I'm showing here in this picture is sort of like a numerical experiment. I'm increasing the horizon with respect to the mesh size from left to right, and I'm showing the assembly time for a non-local operator. So in this case, this is the constant kernel using either sparse matrices or hierarchical matrices. And we see that on the left end where the horizon is uh, only like I don't know, like twice as large as the mesh size. We see that the cost to assemble into a sparse matrix is quite low, but as we increase the horizon size, the cost sort of like keeps on going up. On the other hand, if we assemble using hierarchical matrices, the cost effectively stays more or less constant. And there is a sort of break-even point that, I mean, I determined the sort of break-even point for both in 1D and in 2D, and I gave this here, but there's no hard and like fast rule, like, okay, this is what it should be, what this break-even point is. In practice, it will depend on a lot of things like the type of the kernel, because that influences the types of quadrilaterals that we can use, what types of quadrilaterals we're using, and how efficient your implementation is, both for like the sparse matrix assembly and the hierarchical assembly. So these are sort of like more sort of like rough guidelines where this happens to be the case for my code. What we do see though is that the break-even point sort of is dependent on the dimension of our domain. So if we're in 1D, this seems to be a lot further out than in 2D. And if I have not run this example in 3D, but I would expect it to be even lower than that. Next slide, please. All right. So so far we have looked at geometric multigrid, and what we didn't like is that as a user we have to specify this entire like hierarchy of nested meshes and then assemble all the corresponding operators. So that's not really very user friendly. If really only we want to solve a single linear system, why do we have to assemble all these other linear systems as well? That's not really fun. So what we'll try to use instead is so-called algebraic multigrid, where the difference is that so what algebraic multigrid is trying to do is only take the actual linear system that we're trying to solve, and then based on the information that is contained in that system, try to derive this entire like hierarchy of coarser approximations of our operator. So typically what this then needs as inputs is, well, the matrix itself that we actually want to solve, and then some additional auxiliary information. So what is very common is that you need to pass the physical coordinates of the unknowns. Well, that's not a big deal. That's easy to assemble. And then something like the near null space. So in our case, that's just the constant function. If we were to do paradynamics, this would be like rigid body modes or something like that. And then what algebraic multigrid is trying to do is construct these transfer operators going to a coarser mesh purely using this algebraic information. So it will look at sort of like the matrix graph or like the sparsity pattern of the operator that we're considering. And then in the next step, once we have constructed this mesh transfer, we will then form the matrix on our sort of coarser grid simply via this triple product with our stiffness matrix. And so we can then sort of like recursively go through and construct coarser and coarser meshes. Now, the problem when we want to do this for non-local problems is that, well, we don't have a sparse matrix. So none of these sort of nice graph algorithms will just simply apply. Instead, we have a hierarchical matrix. But even if we were thinking like, okay, maybe we can like put this in as if the horizon isn't all that large, maybe we can put in our a sparse matrix. It still might not work all that well because these problems have like still significantly more density than a classical PDE problem. And so some of these graph algorithms might actually be quite inefficient at this point. Next slide, please. All right, so we have to come up with some other idea how we can construct an algebraic multigrid preconditioner for our non-local problem. And well, we make our life simple. We just say, let's assume that we have some auxiliary matrix that is sparse and that we can use to construct this hierarchy of transfer operators. Then we can go ahead, construct our entire hierarchy, and then we can go back and actually apply these transfer operators that we just constructed to the operator that we actually care about, our non-local operator. And so, well, that's great. But then now we have to say, well, what is a good auxiliary operator, a sparse matrix that we can use? I mean, it should contain enough information about the system that we actually care about. And so, what it should know about is like something about the mesh, something about the coefficients of our problem, maybe ideally even something about the kernel. And so the sort of like auxiliary operators that we've been looking at, sort of like the first one was, oh, let's simply use the PDE Laplacian. That is a sparse matrix. And at least this one knows something about the mesh. It doesn't know anything about the kernel function itself of the non-local operator that we care about. And the next option would be to use sort of like the near field matrix of our hierarchical matrix, apply a bunch of filtering to it, and then build a distance Laplacian on the sort of remaining graph of this operator. So that also is a very sparse version of our problem. Next slide, please. All right. So the second topic that we need to address with this is that we need to be able to perform this sort of triple product of like a sparse matrix, hierarchical operator, and then sparse matrix to form our coarse grid operators. So if we have our hierarchical matrix written out using the representation that I showed earlier, using all sparse matrices, well, then it's relatively easy to see. If we just multiply it with sparse matrices from both sides, we recover something that that essentially has the same form, and again is a hierarchical matrix. So that's great. So essentially what this says is that this sort of like family of hierarchical matrices is closed under like multiplication with sparse matrices. What that means though is that we effectively then reusing the same sort of compression as we were using on the finest level of our multigrid hierarchy. And in practice, this ends up very quickly being inefficient because we need to recompress our operator to stay sort of like within a nice complexity envelope. So we'll have to do some amount of recompression. Next slide, please. So the question is like, okay, so how do we want to recompress our operator on coarser levels of our multigrid hierarchy? And so, I mean, a priori, I don't know how to do this. So I decided, okay, let's just look what would geometric multigrid do. So what I'm showing here is on the left is an operator assembled on, again, a 1D operator assembled on a fine level, and on the right on a coarser level. And what we see that some of the blocks sort of like seem to like match up. On the right, the sort of like the number of the sort of like the thickness of the red blocks, the ones that are in the near field, sort of like increased a little bit. So we sort of merged some of the smaller blocks on the left side into the near field on the right side. And we also see that, well, you might not see this because it's really small. The small number in these blocks indicates the rank of the low rank approximation for these different blocks. And we see that that got decreased on the right side on a coarser level. So our recompression strategy then will be, I mean, we won't be trying to deal with the rank and sort of like reduce the rank of our approximation. We'll just keep the same rank. But what we will do is we will move the smallest blocks into the near field and sort of like multiply them out and like add them into our near field matrix. And that is our like really simple recompression strategy. Next slide, please. All right. So, I mean, This is a very full slide. I'm not actually going to talk about this much. Effectively, the upshot is that this entire recompression strategy just again amounts to doing a lot of sparse matrix additions and multiplications. So in the end, you don't really need any additional code to do this. You probably already have all the ingredients for that. Next slide, please. All right. So talking a little bit about the implementation itself. So there are a couple of components that go into this. So the first is my own code, which is called PyNucleus, which deals with all the assembly of these non-local operators. And then for the entire like solver part and all the algebraic multigrid, I'm reusing components from Trilinos, from the Trilinos library. So for example, Mulu for algebraic multigrid. And the nice thing about that is that all of this then builds on top of the Cocos programming framework, which means that, which is a performance portability layer, which means that this code can run both on sort of classical CPUs, either in sort of like a classical serial way or in a shared memory OpenMP fashion. But it can also run on GPUs, so something like NVIDIA or AMD GPUs, and can also run on some of the newer Intel GPUs as well. All of this is MPI distributed, so distributed memory. And yeah, next slide, please. All right, so first example is again my 2D sort of like a disk, and what I'm showing is a weak scaling. Now using algebraic multigrid, we increase the number of MPI ranks proportional to the problem size, and what I showed this time as well in the sort of like the middle of the table is how large would the stiffness matrix be if we actually assembled it into fully dense format. Obviously, in practice, we never do this because it's a terrible idea, but just to compare the size of this operator compared to the hierarchical matrix format, we can see that instead of having a matrix that's, I guess, 4.7 terabyte, we get something that's 20 gigabytes. So it's a lot smaller. Then the number of iterations for algebraic multigrid on the right, we see that it's pretty much constant, which is what we want. And this in this case, I'm showing both the sort of like the PDE Laplacian as our auxiliary matrix and the distance Laplacian, which also knows something about the kernel function. The number of iterations doesn't really change much, and the reason for that is that our kernel is still simple enough that it doesn't actually matter all that much. I also showed the time to solution for these different for the different problem sizes, and we see that it sort of like grows again logarithmically, which is the expected growth. Next slide, please. All right, just for comparison, so if we would still use hierarchical matrices, but we didn't use a scalable solver like multigrid, how much time would it take to solve this problem then? And we can see, well, obviously, if we don't do this, then yes, our solve will take a lot longer. So using something like algebraic multigrid definitely does pay off. Next slide, please. All right, so we can also then use this for problems where we essentially try to put more unknowns close to the boundary to better resolve the sort of like very steep behavior close to the boundary. Algebraic multigrid still works just fine. I mean, again, this is a weak scaling example. So as we sort of like refine our problem, the aspect ratio between the largest element size and the smallest element size that I have like in the second column of this table sort of like it keeps on going up, which makes sense. Algebraic multigrid, the number of iterations that we see on the right, still more or less constant. The timings could be a little bit better. I mean, they have to go up due to this logarithmic factor. That makes sense, but they're growing a little bit too fast for my taste. And we're blaming this again on load balancing. I mean, you can imagine that sort of like the sort of like the ranks that cover some part of the boundary of our domain have to work a lot harder than the ranks that are on the interior of our domain. Next slide, please. All right, so far all the results that I showed they were on CPU. Now sort of like the same problem again, but now running on GPUs. These GPUs they're quite beefy, and so we can run the problem a little bit larger, up to somewhere like 3 million unknowns. And again, we see that we recover more or less constant number of iterations. The solve times also look quite good. And sort of like this, I think this is the largest problem that we've run for this so far. So somewhere around 3 million unknowns, and the savings in terms of memory we get up to like a factor of 1,000 due to the fact that we're using hierarchical matrices. Next slide, please. All right. Actually, yeah, let's skip the domain decomposition part. This is sort of like work in progress, and go to the next slide right away. All right. I mean, I'm sort of running out of time, but I do want to like get in my advertisement slide. So this is the slide for PyNucleus. So this is a Python code, but all the computational kernels, they're written in Python, which essentially compiles down to C or C++. It's compatible with NumPy and SciPy. It can solve problems in 1D, 2D, 3D. It's MPI distributed, and it has a lot of like different finite element spaces implemented in it. It also has the assembly of not only non-local operators, but also local operators, because chances are you don't really want to only solve non-local Laplacians, but maybe some sort of like advection diffusion sort of problem. Has a lot of solver options. It has the assembly into these different matrix formats, so either sparse, fully dense, or hierarchical. And you can try it out by simply going to the URL that I have there, and sort of like run it in the cloud, so you don't have to install it right away. If you want to install it, you can also do that. It's somewhat involved, but I have some instructions for that. So next slide, please. So here's an example how to solve a non-local problem or non-local Laplacian in 20 lines of code. I am trying to make it somewhat simple. Obviously, I mean, this example does not use any MPI parallelism, so it can actually be quite quick. So we're getting a kernel function, we're getting a mesh on which we want to solve our problem. We're setting up in line 12 a finite element space for our problem on that mesh. We're then constructing a load vector or a load function first, and then we're assembling the load vector corresponding to that in line 14. We're assembling the stiffness matrix. We're getting a vector for our solution. We're constructing a solver in line 19. We solve the problem, and then we plot the solution. It's really as simple as that. Next slide, please. All right. So in conclusion, I'm hoping that I've convinced you that while the systems arising from non-local equations can often be quite dense, they're not structurally dense, and so you can recover a lot of sparsity from them, which means that assembly and operations with those matrices can be done in order n log n operations. In terms of solver options, the usual suspects still work and are optimal. So multigrid and domain decomposition for these sort of elliptic types of problems, they still work just fine. There are some twists that you have to sort of apply to like be able to use algebraic multigrid. But the nice thing about it is that a lot of these things they leverage already existing code, and so you in the end we don't have to write that much code to be able to solve these non-local problems as well. As sort of an outlook, I've shown you numerical examples essentially with constant coefficient problems, apart from this one case where I had like this varying fractional order. But for coefficient variations, especially algebraic multigrid should be really good for that. So we should run some examples for that. I've shown you examples with a lot of hierarchical matrices in it. Not so much the case where the horizon of the non-local operator is quite small, but all of these techniques, all these solvers, they should still work just fine. We obviously also want to like look at more general boundary integral equations and use AMG for that. Then recently we spent quite a lot of time looking at inverse problems with space varying fractional Laplacians, and also doing a lot of uncertainty quantification and Bayesian inference. So with that, well, thank you for your attention, and I'll take questions.
Thanks, Christian. That was actually pretty nice. Bravo for bringing all the scientific computing tools to the fractional non-local worlds. This presentation was actually quite very thorough. I greatly enjoyed it. So for questions, please raise your hand. Please raise your hand. I don't quite see any raised hands. So I have one or two trivial questions, if I may. Uh, so when you had this matrix decomposition into near and far
Mhm.
field, uh, what did you imply by that? Because are you just looking at the matrix, uh, or you decided, okay, what exactly is the near and the far field
Okay.
imply?
I mean, you can almost think of it like in terms of like the distance in your physical space. So if you look at some particular degree of freedom, all the sort of like other degrees of freedom that are like really close to it in physical space, and the interactions between them, that's going to be a near field. But things that are sort of like over a longer distance, you will consider it as far field. Now, obviously, like what is near field and far field will depend on a bunch of different factors, like how refined is your mesh, for example, or what is your actual like physical domain looking like. So it's but in the end, you're distinguishing between near and far field based on the actual distance in the domain that you're looking at.
I see. My confusion was because this is a non-local operator, so everything is long distance. But I see your point. It doesn't has to. It's not dependent on what kind of operator. It's just like you're
Correct.
sitting on
I mean,
one.
yes,
Yeah,
you're interacting over a long distance, but it doesn't
yeah,
mean that you can't like split this into like these two different categories.
yeah. Exactly. You're just sitting at one node and you're trying to figure it out. Like, okay,
Mhm.
how I should, how should, and whether or what kind of operator acts on it. It's a different story.
Yeah.
I see. I see. Did you work with fast multiple method as well? I believe Leslie Gringard introduced it, right?
I mean, it's sort of the same concept. This whole hierarchical matrix business is sort of like a generalization of that.
Okay. Okay.
I mean, fast
Uh,
multiple method in some ways is like very much tied to like electrostatics and
mhm,
physics, where you sort of like think like, okay, you have like a bunch of like particles over here and a bunch of particles over there, and you sort of like try to sort of
mhm.
collectively approximate their interaction, which is sort of like the same as saying, okay, we're forming like a low rank approximation of this sort of like interaction.
I see. I see. I see. Fair enough. Fair enough. Okay. So with this hierarchical matrix and with this, initially what you had was a dense matrix, and then you were able to sparsify the matrix, right?
Well,
Yeah.
I mean, the thing is, you never want to like have to assemble this fully dense matrix.
Matrix.
So you sort of want to be able to do this on the fly without ever going to a fully dense format.
Mm-hmm,
And
mm-hmm,
so that point is, I mean, there's different techniques for doing this. Generally, I mean, one of these methods relies on you simply like sample out of these sort of like far
mm-hmm.
field blocks, and then based off of the sampling, try to construct a low rank approximation of that block. What I do instead is because I know a lot about the form of my operator. I mean, I know it's like a sort of double integral, and I know the kernel, I know a lot of things about it. I'm using a sort of like a tensor or like a tensor interpolation of this double integral, or like
Mm-hmm.
of the kernel function within that block. And what
Mm-hmm.
that means is that effectively this double integral sort of naturally breaks up into two single integrals, coupled
Mm-hmm.
by this sort of like interpolation of the kernel function. Um, but that obviously assumes that I know a lot more about what my operator actually is, which
Okay.
I mean, I'm in a sort of like restrictive enough framework that I can do this sort of like independent of the kernel function itself, which is quite nice.
Okay. I think I get the high level idea, but in general, I think I'll have to go a little bit deeper into the topic itself before I can uh,
Yeah, I mean,
uh,
there's a lot of like
welcome.
sort of points that
Yeah.
become very quickly quite technical once you
Yes.
start looking at all of them individually. But I try to sort of like convey, focus more on the sort of
Hmm.
like idea and not so much on the technical details.
Yeah. Fair enough. Fair enough. Appreciate that. At least you gave us a very nice starting point. Yeah. Yeah. In the initial slides, you had the solution represented as double sum. Uh, uh, sum of edges and
Yeah.
sum of elements. So the second sum was on the elements where you had the support for that particular point, right? That would make
Right. So the second sum is effectively the term that you get from like the outside of your domain, um, that you sort of played back via this Gauss trick to the actual like surface of the domain. Now, this assumes some sort of special volume condition, but there's like different variants of this trick that effectively you can sort of reduce the problem overall always to a bounded domain.
okay. Let me just go. Can I just go through that slide?
Sure,
Uh,
yeah.
uh, uh, it's much before. Mm, Okay. Uh, where was this? This one. This
Hmm.
one. So this one, the second sum should be on the domain on the support of it, right? Uh, uh,
Right. So, I
so
mean, you have like one sum over the elements. K are the elements of
yes,
and E are the sort of like the edges that are like on the
they are
surface
the.
of the domain.
Okay, okay, but that's wherever the support is touching those elements, not all the elements.
No, I mean it really is it is a full on double sum, and this is like due to the non-locality of the problem.
Okay, okay, okay. No, okay, because I would because my initial thought is that if I'm sitting at point X and then I draw a delta, that's where my non-local operator has a support. So
Oh,
so
okay, sorry. Maybe I misunderstood your question. Yes, I
mhm,
mean obviously, I mean so even if we look at the first sum, if gamma is outright zero between two elements k and k tilde, then yeah, we don't need to like include this into the sum.
mhm.
I mean, to some extent, I mean, you can see this doubles. I mean, in the case where the horizon is infinite, yes, you have to like take every sort of like element combination into account. But if obviously if the horizon is smaller than that, then no, you don't have to do that. Yeah, that's correct.
I see, I see, I see. I'll probably have some more questions for you, but I'll
Mhm.
go through a bit of your work and then I'll probably get
Yeah,
back to you.
please do. Yeah, I mean, I'm happy to like get emails.
Yeah, because I'm also working on a similar effort. If you're acquainted with Zainuri's work and on polyfractonomials, uh,
Hmm.
so I recently extended to general fractional operators and
Hmm.
introduced the Jacobi convolution polynomial, which is going to be applicable to all of those things. So
Hmm.
I have some nice theory, but the missing part for me would be all of the structure that you have for the code,
Hmm.
and you have
Yeah, yeah.
already
Don't
implemented.
hesitate to like contact me. I'm more
Yeah,
than happy to like answer
yeah.
questions.
Yeah, thank you, thank you, thank you. Yeah, that this was actually very nice. Uh, okay, I believe that this is also a good point to close this talk. So let me stop the recording. Uh, stop the share and recording. How?